Today we're going to be focusing on a company called Turbine Technologies in southwest Wisconsin in the U.S. That does some very interesting applications using our real wax multi-jet printing technology. I am talking to you from Rock Hill, South Carolina at 3D Systems, and am glad that you joined us. I think you'll find the information in this webinar to be very informative, both in the specific application but also in showing how these disruptive and transformative technologies can really provide significant value when employed in unique and creative ways, both in production and in prototyping. 3D, just before we get started, I wanted to give you a quick overview of 3D Systems. 3D Systems is a leading provider of 3D printing-centric design to manufacturing solutions. And we've got a long history of technological innovation and advancement. The whole 3D printing industry was invented by our founder, a gentleman named Chuck Hull, who invented a process called stereolithography back in the 1980s and founded 3D Systems. And over this period of time, into the 90s and even into the 2000s, we continued to innovate with different technologies. We have a wide number of different ways we do 3D printing that enables us to use different materials and to apply this to different application use needs. We are a global company. We do business in all around the world. We have our size of company is about 1,300 employees. We call them teammates. We have 7 different print engine technologies that we employ, with over 100 performance materials designed to work in these printers. We continue to expand that technology platform. One of the hallmarks that we are proud of is that from a richness of our technology base, we have as many patents as we have employees. We cover more than just 3D printers because we understand that whole digital thread that works all the way from your design all the way through the part manufacturing needs to have continuity, and we are developing the infrastructure so that you can have seamless productivity through your design efforts. We have design productivity tools on the software and design end that feed into our 3D printers. We also develop the majority of the print materials that are used in our printers. We also have a on-demand parts manufacturing capability, so even if you have your own 3D printing shop and your own equipment, you can have access to the entire range of both additive and subtractive manufacturing capabilities through our on-demand parts, which we call quick parts. In our 3D printer portfolio, we have printers that range from $1,000 all the way up to high-performance systems that are much more expensive. We have consumer printers, we have professional-level, in-office friendly printers, and we have, at the high end, we can print in direct metals, we can print selective laser sintering, nylon, very abuse-resistive products, and we have a range of products in between that cover the scale. So we really try to match the right technology to the right application and right budget requirements that you may have. When we look at opportunities for people to enjoy 3D printing and to get the benefits that come with 3D printing, such as collapsed design cycles, faster production, custom manufacturing capabilities, prototyping applications, we have different printers that serve these in ideal ways. At the beginning of a design process, communication is very important. We have full-color printers designed for communication modeling, which can help you make good early decisions before you move further into your design process. As you're in, mechanical design, design validation becomes very important, and we have systems that are ideal for doing validation testing and even moving into pre-production tooling to help do bridge manufacturing or get you into production faster. We have fab-grade capable 3D printing technologies in both plastic and metals that can do in-use production, and our systems are very well tailored for custom manufacturing and mass customization in in-use manufacturing. I've mentioned communication modeling. That's what we call concept modeling, and that's where you're comparing design concepts where you need to look at alternatives side by side to make good decisions. And we can do full color concept models that can help you to make good decisions early, allowing you to have not only better designs and make better decisions, but also to eliminate or reduce costly design changes that may come later, which can become much more expensive to make later in a design process. When you get into prototyping, functionality becomes important because you're going to want to test your designs, know that these new inventions work as you intend them to. And so prototyping during the design process allows you to do more iterations and to do more testing so that you can discover improvements early before you've committed to more expensive tooling and manufacturing capabilities. Here you're testing form and fit. You can get hands-on feedback, and you can really prove out those design ideas that may be revolutionary in your industry, but you can test them in real applications so that you make good design improvements and move your designs forward. As you get toward moving designs and developments toward manufacturing, you're going to want to do both alpha and beta runs on your product. But you also have that period of time where tooling is being manufactured that can take additional time until you can get into market. So you can do not only early production for beta testing, but you can also do bridge manufacturing to collapse that time schedule to manufacturing. And by doing those early production runs, it can give you the confidence you need to make those more significant supply chain commitments and investments that you have as you move toward mass production. And in manufacturing, we have a lot of applications being done. We call it digital manufacturing, and that can be both direct or indirect. Here, our printers can provide the kind of accuracy and precision that you need, and they can do that basically with almost unlimited geometry capabilities. So you have the design freedom to really look at your designs and push the envelope in terms of capabilities to have step change performance improvements. Or you can reduce weight, for example. Printers are able to print structures in honeycomb that you could really not practically do any other way, which can help you reduce weight, which is important in a lot of applications, especially in automotive and aerospace, where weight translates directly into fuel efficiency. You can use this to do smaller, more mass-customized production. You can have shorter production runs because there's no tooling involved with digital manufacturing. I also mentioned indirect manufacturing, and that's really in the realm of today's discussion about what Turbine Technologies does, because they're doing wax patterns that are printed on 3D printers to enable a digital casting application to get metal components faster than traditional methods. The specific printer that will be highlighted today is in our ProJet 3500 3510 series of printers that uses an inkjet process. We call it multi-jet printing to produce real wax patterns that can go into standard direct investment casting applications. And these are true waxes that are printed and can fit into traditional casting methods the same way that casting waxes are used today. And they are high precision, high performance materials and printing resolutions that enable this application. And so that's a little summary from 3D Systems. I am going to introduce now our presenters from Turbine Technologies. Tony Kutrib will be leading this. He's the Vice President of Turbine Technologies. He's joined by his colleagues, Mike Kutrib, who is with a sister company, Kutrib Research, and also Perry Kuzner, who is a business development manager at Turbine Technologies. And so I will now ask my moderator or my organizer to pass the presentation capability over to Toby.
Well, hello everyone. This is Toby Kutrib. I'm the Vice President of Turbine Technologies, and I'm one of the 5 family members that guides our second-generation technology-driven business. I'm joined this afternoon, as Buddy said, with my brother Mike Kutrib and Perry Kuzner. Mike is the president of our sister company, Kutrib Research, and Perry leads new business development at Turbine Technologies. Mike and Perry are both mechanical engineers, and they're very hands-on with our in-house manufacturing and prototyping. Actually, all 3 of us continue to gain experience with 3D Systems rapid prototyping and want to share our success with this amazing technology. Okay, well, we'll dive into that shortly, but first I'd like to provide you with a brief synopsis of our company's background. Our family's been in business since 1967. My father and mother founded the company shortly after immigrating to the United States from Germany. My father completed his education in Berlin, and he holds numerous patents in areas related to combustion and thermal fluid systems. Our company's general theme has always been to utilize engineering talent to develop and manufacture innovative devices. My 2 brothers, Mike and Tom, and I joined the business full-time in the mid-90s. Turbine Technologies serves the educational marketplace. We develop, manufacture, and support a line of hands-on educational systems for engineering and technology programs. Our customers include hundreds of engineering colleges worldwide. They include United States Naval and Air Force academies, Princeton University, Stanford University, and as you can see on the slide, quite a few others. Our educational devices provide students with unique hands-on experiences. Our product lineup includes an instrumented jet engine, a miniature steam turbine power plant, and even a wind tunnel with a fully functioning wind turbine electrical genset. The full product lineup can be viewed at turbinetechnologies.com. We've always been a vertically integrated company that efficiently develops product from soup to nuts. We take concepts from initial idea to a finished product under one roof. That's the founding principle that has allowed us to offer our customers cutting-edge products and at a very affordable price point. Our northwestern Wisconsin facilities include 42,000 square feet of space, and we've got a 7-acre site adjacent right next to the Chetek, Wisconsin airport. We're about a 2-hour drive east from Minneapolis, St. Paul. We continue to stay ahead of our competition by investing in cutting-edge technologies. We operate a complete mold and machine shop with 5-axis milling capabilities, along with numerous software tools that support the design, analysis, and part manufacture. And to that point, for this presentation, we operate one of the few super LA vacuum investment casting foundries in the country. It's our continual drive towards increased efficiencies that led us to 3D Systems. So, okay, at this time, I'd like to turn the presentation over to Perry Kuzner. He'll be walking us through Turbine Technologies' foundry process, and that's going to provide some substantiation of the original time savings claim in the webinar invitation email that you received. Perry?
Hello, everyone, and thank you, Toby, for your introduction and overview. My portion of this presentation will focus in on just one of our educational lab products, that being a jet engine, and how we utilize our superalloy investment casting process in the development of that engine's superalloy axial flow turbine wheel. Turbine Technologies' gas turbine lab system gives engineering and technology students an extremely unique opportunity to operate and analyze a real jet engine. Looking at the slide, you see that the cabinet that we have depicted holds our own SR30 turbojet engine and all of the subsystems for that engine's operation. It's also equipped with conditioned temperature, pressure, and flow sensors for computer data acquisition. That's also on board the system. You know, although our gas turbine lab system is typically found in educational settings, it's also used in a variety of research areas. One, for example, is the development of alternative fuels. I'm going to play a short video that describes a recent effort by the U.S. Department of Energy's Advanced Research Projects Agency for Energy, which is ARPA-E for short, and them collaborating with North Carolina State University in terms of biofuels research. It'll give everybody an idea of the turnkey and dynamic nature of our gas turbine lab.
I'm Eric Toon. I'm the Deputy Director at the Advanced Research Projects Agency for Energy, ARPA-E. The Electrofuels program is designed to develop efficient means of converting solar energy into stored chemical energy in a liquid fuel that we can burn in a vehicle.
The fuels that we need to make that are renewable really need to be two things. They have to fit with the current infrastructure, so they have to be compatible. And in addition, we really need to make them at a cost competitive point to the petroleum. And that really allows the biofuels or the renewable fuels industry to compete and to grow on its own merits. So NC State is another collaborator that also is funded by the ARPA-E program. And they have a technology that allows them to convert fatty acids into renewable diesel. And so we've actually been producing renewable fatty acids from hydrogen and carbon dioxide in our fermentations at OPX. So we've actually separated out the fatty acids, which are long chain molecules that are energy dense, and we've purified those, and we're sending the fatty acids to NC State for their conversion to fuel.
We start with a fatty acid, which is, in this case, is solid at room temperature, and we go through a series of thermocatalytic processes. And then if we are going after an aviation fuel, we want some aromatics in there for materials compatibility within the engine. And so we end up with a fuel that's, has a high flash point. For safety, has a low freezing point because you don't want the fuel solidifying at 30,000 feet. And so this is virtually indistinguishable from petroleum-derived JP8. And that's where we started, what we set out to do.
That is the collaboration, and again, that's just one of the very small elements we're involved with here at Turbine Technologies. Okay, now that we've walked through kind of a top view of our jet engine product, I'd like to continue to drive down on the engine itself and ultimately arrive at the traditional manufacturing method that we use for one of the key components of that engine, and that would happen to be the axial flow turbine wheel that is used in that engine. The turbojet engine that we have, the SR30, is comprised of a number of complex airfoil components. They include a 5-axis machine centrifugal compressor, a vane diffuser, a bladed nozzle ring, and of course the aforementioned turbine wheel. It so happens that the component under the greatest amount of stress in that engine is that axial flow turbine wheel. And that's what I'd like to spend the next couple of minutes talking about. The turbine is comprised of a bladed disc or blisk that is cast as a single part. It operates at speeds of up to 85,000 RPM. Compare that with your car sometime and see what that operates on. Usually that's about 2,500 RPM, so this is quite a bit faster. It also does so in a high temperature environment that can cause this turbine wheel to glow red hot at times. At the engine's design speed, each blade can be under a load of up to 2 tons. Obviously, this requires a special material, and the alloy that we utilize here at Turbine Technologies is a high nickel content super alloy. This alloy has excellent creep properties and is standard in the aerospace industry for this type of high temperature, high load application. Even though the material, which is designated CM247LC, exhibits excellent properties, it's very difficult to work with from a manufacturing standpoint. Machining methods would not be suitable, would not be a suitable solution for manufacturing this turbine wheel. The material is nearly impossible to machine, and second of all, if you look at that thing, you see the geometries that are involved. It really makes it almost impossible to cut those geometries with standard mills or lathe operations that we would typically use in a machining setting. So simply put, all of the world's turbine blades are only manufactured using one method. That is, they're all cast out of molten superalloy. The methodology is called either an investment cast process or is also known as a lost wax method. For those of you with a background in material science and or you're involved in foundry operations, the following will be rather fundamental. But I'd like to walk everyone through the basic steps in order for you to gain an appreciation for the methodology, which will be necessary to understand the latest process efficiency gains made possible by the 3D Systems rapid prototyping. To begin with, the material melts at well over 2,500 degrees Fahrenheit. Things get even more difficult when you realize that the material itself cannot be melted in the presence of atmosphere. If allowed to oxidize, the superalloy will lose all of its mechanical properties. So therefore, our foundry is equipped with a vacuum chamber that allows the poured metal to occur in the absence of an atmosphere, essentially no atmosphere. So in other words, the molten metal is poured in an environment not too different from pouring metal in outer space. So let's step through the process of creating a turbine blisk. The first step is to calculate the flow energy values and blade shapes that will maximize the turbine power output. We use a variety of software pieces in-house here to help us with these calculations, and then a solid modeler to generate the proper blade shapes. The second step moves the finished part design from engineering to the mold shop. An aluminum wax injection tool needs to be manufactured that will create an exact wax replica of the actual part. The mold design is complex and requires shrinkage calculations and a variety of manufacturing methods. These might include die sink EDM, wire EDM, milling, grinding, lathe work, etc., etc. A lot of different things that are done to make that part. Even finish polishing is required. Within the traditional process, injection mold manufacture is costly. Skilled labor is needed and it's very intense. And once completed, the injection tool is permanent and can obviously only create one shape. You can see a portion of the complex mold on the left picture in the slide, and the wax patterns of the turbine wheel on the right side made from that mold. The third step in the process includes wax inspection, and then the application of a ceramic slurry to the wax pattern. Successive dip coats are applied to the wax pattern in order to build a ceramic shell. So you see on the left side there a fluidized bed adding coatings of ceramic, and on the right, the coated turbine wheels. The fourth step occurs after a requisite shell drying time. This entails the removal of the wax from the new ceramic shell. The entire pattern is placed into a fancy pressure cooker or steam autoclave. The wax is melted out of the ceramic by way of application of superheated steam. The ceramic shell now exhibits a negative cavity of our desired part and is ready for the final step in the shell building process. The fifth step is the firing of the shell. The ceramic shells are placed into a gas-fired burnout furnace where they're brought up to a temperature of 1800 degrees Fahrenheit. So any residual wax that's left in those shells is burned out. And this step also serves as a preheat prior to the shell being placed in the vacuum metal pour chamber. Now that we've described our traditional investment casting process, you can begin to see that a large percentage of the complexity of this process is in creating that wax part. As you will soon see, 3D Systems offers a game-changing technology for that very process. At this point, I'd like to turn the presentation over to Mike Kutrib. Mike is the president of our sister company, Kutrib Research, and Kutrib Research is strictly engaged in the development of small gas turbine engines for future use in areas that include unmanned aerial vehicles and high-speed targets. I'm going to turn it over to Mike. Mike?
Good morning. Thanks, Perry, for your excellent overview of our traditional foundry operations and our process in the foundry. So to provide some background on my activities here at Kutrib Research, turbine technologies, close affiliation with academia, with our gas turbine lab, the system that Perry's just described, led to increasing requests for us to become involved with small gas turbine engine development. And in order to provide focus to that activity, we did spin off a new company by the name of Kutrib Research. Our first project was with the Defense Advanced Research Projects Agency, or DARPA for short. More specifically, we were under contract by one of the prime competitors, Honeywell International. We were their vendor in the development of a small 50-horsepower turboshaft engine that was designated PT-50. The engine was designed to power a pilotless unmanned aerial platform with a moniker of Organic Aerial Vehicle, or OAV for short. OAV was actually a quantum leap ahead of present-day technology. It was intended to take off and land vertically, and it had a very advanced sensor package that allowed it to provide automatic collision avoidance, battlefield damage assessment, laser targeting, and even self-tasking. The program was a small part of the Army's net-centric warfare development effort, and I'd now like to play a short video clip of that concept, just a short animation. Okay, the concept animation you just saw actually ultimately led to a completed working prototype. The vehicle pictured above was developed for aerodynamic validation testing at NASA Langley, and following those tests, it was shipped to our facility in Wisconsin for engine integration. Upon its arrival back here in Wisconsin at our facility, we installed our newly developed PT-50 engine and ran full flight profiles within this Ironbird mock-up. And I'd like to play a short video of that activity, the engine running within the wind tunnel mock-up. And I'd like to point out that we should keep in mind that besides all the major bladed engine components that typically would need tooling, Those components were manufactured via 3D Systems wax printing technology, but also airframe parts, all the white components that you see on the vehicle, were manufactured by a 3D Systems SLS machine. So rapid prototyping on this project assisted in both airframe and engine development and shaved hundreds of thousands of dollars from the project and tooling costs alone. Let's watch the engine run on the vehicle. Okay, so our efforts with Honeywell were very fast-paced and created a real pressure to perform on schedule. Quarterly reviews always came faster than desired, and weekly conference calls kept up the pressure. That environment led to all kinds of need for more rapid development capabilities. Sometimes it wasn't even an issue so much being constrained by budget, but more so of meeting milestone requirements. So therefore, we invested in a number of new software tools and also met individuals from 3D Systems. Back in 2006, we purchased our first rapid prototyping machine from 3D Systems. It printed polymer or plastic parts. It was a great start to providing us with quick-built, hands-on articles. However, our real desire at that time was to use the plastic part as an investment pattern to fit into the foundry process that Perry had just described a little bit ago. Unfortunately, when we tried that, the coefficient of expansion on the material produced cracks in even our strongest shells. 3D Systems provided a partial solution in a software upgrade that actually created voids within the plastic build, the honeycomb type of void in the part. This allowed the plastic part to cave in on itself as it began to melt and did allow for some success in casting. But the technology at that time had some drawbacks in that foundry process, primarily as I had described with the shell cracking. But not long after, we were approached with a brand new technology. 3D Systems visited and introduced a machine that they said would actually print investment-grade wax, wax material that would melt out of our shells, just like our current injection wax. And we were obviously pretty excited about that with the concept of doing development without creating the permanent molds that Perry described. It was something we really needed to see, and we did. The slide that you're viewing here is our 3D Systems Rapid Prototyping Wax Printer as presently installed in our prototyping lab. We're presently under development of a brand new 300 shaft horsepower turbine engine. It's a giant leap forward for us into a much more complex and capable engine. As you can see, and based upon Perry's presentation, a simple part, say for example the geometry of a hockey puck, would be easy to produce via traditional mold making process. It's a simple cavity and it could be done quickly. However, as part geometry increases in complexity, tooling and molds become very expensive to generate, and our new engine has plenty of complex shapes. The Kutrib Research X engine exhibits a 4-stage compressor section and provides us with an excellent example of how rapid prototyping saves the day. Here's the component in question. This is our X engine's compressor stator. It consists of 4 axial blade rows. Using a traditional manufacturing method, we typically create 8 injection tools and also an assembly fixture. The mold, tool design, and manufacture would require about a month and a half. The only reason it would be that fast is the fact that we maintain those capabilities in-house. If we were to farm the project out, it could easily approach a 6-month time frame, and you could only imagine the cost also. I mean, it would be well into a 6-figure range on costing of that tooling. With the use of our 3D Systems wax printer, however, we literally printed 2 parts rather than creating molds for 8. The part printing required only 18 hours, and it occurred basically unattended. It built the entire case around the clock and in the dark. Also, if we don't like the outcome, we can easily tweak blade geometries and reprint within the next 18-hour period. Following years of traditional mold making, this is truly sci-fi kind of stuff. And we're very proud of this slide that you see in front of you. This is our new X-Engine's finished axial flow compressor section. It literally is made up of 3 parts. 2 stator case halves that feature integral bladed and a single 5-axis machine titanium compressor rotor. This is one of the engine areas where the parts count and cost is greatly reduced by our rapid prototyping capabilities. These are somewhat hypothetical, but within the realm of our internal costs. But I'd like to review some of the comparison between the traditional casting process that we utilize with that of the use of the 3D Systems printer. Using the traditional mold construction method, we calculate it would take us approximately 170 hours to design and manufacture the wax injection mold required for that stator case. It would require numerous steps that include the design of a multi-part mold, machine programming time for 5-axis milling, some lathe work, EDM, etc. Once programmed, we'd need man and machine time for the actual manufacture of the injection tool. And we then need to prove out the injection tool and possibly do some rework. And finally, we could inject the wax. With an average internal overhead rate, including labor, materials, and machinery of, say, $120 per hour, the cost to produce one wax stator case would be $20,400. Now let's compare that effort to using the 3D Systems wax printer. In that case, we'd need to prepare our CAD model for the 3D printer, which is a fairly simple process. We'd transfer the file to the printer and push the start button. Our wax pattern will then build overnight and unattended. Our final step will be to remove support wax from the pattern, and we'd be ready for the pattern ceramic shell build. Total time for this prototyping effort is 18 hours. At the same $120 per hour overhead rate, our cost is down to $2,160 versus that aforementioned $20,000 amount. If we compare a basic savings number just on this part alone, this one component of the engine, you can see we easily achieve a dramatic 90% reduction in time and expense. And we really truly believe that to be a conservative estimate. Our 3D Systems printer literally takes the mold maker out of the loop. It removes all of the complex design steps of tool manufacturing and also eliminates tasks like milling, lathe work, wire EDM, grinding, polishing, etc., as we had stated. It allows us to move through development iterations much faster with dramatically lower costs to boot. This advanced 3D wax printing technology enables both of our family companies to offer clients affordable gas turbine engine development and also leading-edge laboratory learning tools. I hope you enjoyed the insight into some of our activities here at Turbine Technologies and Kutry Research. And this concludes my remarks, and I'll be happy to stay on for questions.
There was a question in here about software, and the question was asked relative to complexity and what type of software allows you to design in unlimited complexity. The reality is that the software tools that people use to design are basically traditional CAD design software tools, and the unlimited complexity really, the barrier to that is more the paradigms and limitations that we've all been trained to put into our designs because we were trained on the limitations of direct or traditional manufacturing methods. And, that's really more less to do with the software and more to do with our own creativity in terms of thinking outside of traditional known limitations of milling or machining type of limitations, and really thinking in terms of if the geometry had none of those limitations, what would be possible? And that's when producing this way, you can, complexity is basically free. A very complex geometry is no more difficult to manufacture on this printer than a simple geometry, simply because of the way printers work. I would direct this question to the guys at Turbine Technologies. The question is, would you just use additive manufacturing to replicate wax models, or have you already improved component efficiency by adding conformal cooling channels or reducing weight?
Regarding cooling on these small engines, it's not typically something that's done. The blade sections are extremely thin as we scale from, say, a full-scale commercial engine. So therefore, with present-day superalloys, the temperature limits are pretty much a function of the limit of the material itself. So we do not do turbine cooling. We do not work with turbine flow passageways.
Here's another question for you guys. It says, I'm interested in knowing what the finishing is like on the parts. There
are a couple of different post-process steps that we take, obviously, from the as-cast, say, for example, the as-cast turbine. There's some precision grinding that occurs on the blade tip for finishing. Yeah, but I'm not sure, buddy, is it a question regarding the RMS finish, like the smoothness of the component or the blading, or is it an actual post-process question?
Well, I'm interpreting this to mean what type of post-finishing do you have to do on the casting to enable it to go in? Is there any finishing, surface finishing that you have to do? That's how I'm interpreting the question.
Okay, it depends on the component. The as-cast finish is acceptable in some structural components. In the case itself, especially say for the, as an example, the exterior surface finish of the stator case that we had shown, that's there's shell removal that occurs, and then there's a bead blast process, and that leaves from a standpoint of just it's just a smooth matte finish. But then when it comes to actual blading, from a prototyping standpoint and a rapid result standpoint, as far as getting the component installed into the engine and into the test cell, there may be, again, no surface finish change from the as-cast bead blast state. However, from the standpoint of ultimate performance, there would most likely be there will be some polishing that occurs on those airfoil shapes.
There's another question that I think is similar to that, asking for a comparison. The question is, what is the resolution difference between wax from a machined mold versus a wax printed version? And so, talking about the finishing or post-processing needed, on those two different scenarios.
Well, again, depending on the component itself, but for example, a lot of the turbine blading nowadays is not run in an as-cast or as-finished condition anyway. Most of those blades also have a coating applied to them, so that would be a post-process, and that affects the surface roughness of the blade itself. And typically those are ceramic-type coatings that increase temperature capability of the alloy. So, I mean, simply put, the as-cast, as-bead blasted scenario coming out of the project at this point is acceptable for us. Now, is it a mirror-like finish? No. And I mean, that's, I'm not giving a quantitative RMS value with this discussion. It's just more of a qualitative, off-the-cuff view of how we do things here on the prototyping side.
Okay. Here's another software-related question. Can we convert SolidWorks drawings for printing? And the answer is yes. One of those that I'd like to address, it was, what kind of accuracy can be achieved in these printers. We have data in applications that demonstrate on this model of equipment that we can maintain accuracies of down to about plus or minus 40 to 45 micron level on this type of technology. Stereolithography, which is another 3D printing technology, it can go to much higher levels of accuracy, to a factor of about 2x that. But these are all very high precision rates on these, and are adequate for applications such as turbine blades, which have a pretty high bar for for accuracies. There's a question here about how does this printer differ from a FDM printer, and an FDM printer is a printer by another, it's predominantly sold by another manufacturer in the marketplace. That's an extrusion process that basically melts a filament of material and draws each layer of the part. These printers are much different than that. The ability to print wax is very unique to this printer. There's no other high-speed 3D printing capability to do wax for wax investment casting as this printer can do. But there's a lot of different printing technologies, and you really have to look at your application and what type of materials that you need and what kind of parts you're intending and what your use case is for the printer. I'll make just the general statement. There's not a perfect 3D printer that does everything the best. You really have to tune the right printer selection with the right application to get the best benefit out of the printer. And certainly there are printers that are more versatile than others. The wax printer is primarily for casting patterns, because wax is not functional to be used as a functional prototype. It is a manufacturing tool. But there's other printers, and even printers within this family, that can print plastic parts that can be used for other purposes. There was a question, have you tested the turbine parts created by RP, and if so, how did they do? I think that that question was probably answered by showing the videos.
Absolutely. That super alloy via the rapid prototyping wax casting pattern operates no differently than our as-cast materials that come out of investment grade wax, just as we had stated in the presentation. The shell itself doesn't, so to speak, understand the difference between an injection wax or a rapid prototype wax. We create the same void to pour that molten metal into.
Okay. There's a question here, where can we get wax patterns if we don't have a printer in-house? Are there shops that offer these patterns? The answer is yes. 3D Systems actually, in our quick parts business, does print wax patterns. One of the challenges in these is really looking at the geometries. If they are very, very thin wall, delicate structures, it's very difficult to ship wax patterns without damage or breakage just from the shipping. It's not impossible, but that would really have to be looked at on a case-by-case basis in terms of practicality. But 3D Systems Quick Parts is available. You can go online, upload data right online, and get printed patterns manufactured for you by 3D Systems. There's another question about what other types of items are these printers being used for casting. One of the very large applications for this has been jewelry manufacturing. That is, all the major jewelry manufacturers use digital production flows now, and the Projet CPX printers, which are the wax printers, are the leading system that they are using in digital manufacturing. We also have a lot of placement for automotive parts, especially in motors. They're making lots of modifications, and they have very short turnaround times that they want to do this. So motor components for automotive, electrical connectors, especially for prototyping of new electrical connectors. They can be manufactured by casting. Medical devices is another area that wax printers are being used for all types of fluid dynamic devices and other types of medical devices and implants. They're used both in human and veterinary joint implants for custom implant work. There are companies that are casting implant stents that go into arteries. So a lot of medical applications as well. And, you know, any traditional foundry items, you know, the whole value proposition of being able to cut out the mold and go straight to the cast, you know, gives a tremendous value in reduction of both time and cost. And so, you know, there's a lot of different areas that that's suitable for. Okay, I'm going to pass the answer to the question about how can you get a recorded copy of this webinar for later, or maybe you want to show it to one of your colleagues or have it available. So either Tom or Catherine, if you guys could answer to that.
Sure, I'll jump in. This is Catherine Scarpolini. So we have recorded the session, and we will be emailing this to everyone who registered within the next day or two.
Great. Well, with that, we're out of time. I appreciate everybody joining, and again, thank you to the gentleman up at Turbine Technologies for taking your time to put together this very interesting and very informative information. And we just hope everyone maybe has some ideas now about how they might employ 3D printing, whether it's doing wax casting or in other ways, to transform the way that you do business and get these kinds of you know, really revolutionary changes in terms of time and cost that it enables. So I hope everybody has a nice day. Again, this is Buddy Byram at 3D Systems, and we're signing off.